Friends, explorers of truth, observers of the immensity that surrounds us, allow me to ask you a question that at first glance may seem as trivial as the blink of your eyes, yet at its core contains one of the greatest enigmas humanity has faced since the dawn of consciousness. What is time? At this very moment, you feel it. It is the relentless advance that carries you from the past into the future, the endless ticking that marks the heartbeat of your lives. But what if I told you that what you perceive as a one-way, immutable current is actually one of the most fascinating and deeply rooted illusions ever constructed by the human mind? Imagine for a moment ancient times, early civilizations, contemplating the movement of the stars, the cycle of the seasons, birth and death, began to weave a concept to organize this perpetual dance. They created calendars, sundials, water clocks, and gave a name to that incessant flow: time. For them, time was an absolute entity, a cosmic river flowing the same for everyone, everywhere, from beginning to end. It was the great constant, the backdrop upon which the drama of existence unfolded. Greek philosophers, with their insatiable thirst for knowledge, already debated its nature. Parmenides, for example, suggested that change, and therefore time, was merely an illusion of the senses. For him, reality was an immutable and eternal sphere. But Heraclitus, his counterpart, argued that everything flows, that no one can step into the same river twice, because both the river and the person stepping into it have changed. In this eternal dialectic, the complexity of what we now explore was already taking shape. For centuries, this intuitive, almost religious conception of time persisted. Isaac Newton, the giant upon whose shoulders classical physics stand, cemented this vision. For Newton, time was absolute, true, and mathematical. It flowed by itself and by its own nature, uniformly, without relation to anything external. It was an empty arena in which events unfolded, unaffected by them and independent of any observer. His universal clock set the rhythm of the entire cosmos, a divine metronome, an unbreakable truth. This was the reality we inhabited for nearly 300 years, a comforting reality in its simplicity, one that allowed us to believe that at least in one aspect, the universe was predictable and orderly. But what if that very simplicity was a trap, a veil concealing far deeper and more vertiginous truths? The first crack in this Newtonian fortress did not come from a philosopher or mystic, but from a young and audacious physicist who dared to question the unquestionable with unprecedented clarity. We are speaking, of course, of Albert Einstein. Before diving into his revolution, let me invite you into a small thought experiment. Imagine you're inside a perfectly smooth train with no windows. How would you know whether the train is moving or standing still? You couldn't. Motion can only be perceived relative to something external. Now apply this logic to time. How do you perceive its flow? Through change, the aging of your body, the movement of clock hands, the cycle of day and night. But what if these changes are not proof of an absolute temporal flow, but merely manifestations of interactions within a far greater network? 20th century physics began to whisper a disturbing truth. Time is not an independent entity that exists by itself. It is something far more malleable, deeply tied to matter and energy, and, as we will later see, perhaps even to consciousness itself. This paradigm shift is so profound that even in the 21st century, our intuition resists it. We live immersed in the illusion of a moving present, a fading past, and an approaching future. But what if everything that was, is, and will be already exists in some way? What if our now is nothing more than a focus of attention moving through a fully formed block of space-time, like a beam of light illuminating successive pages of a book already written? This idea is not mere metaphysical fantasy. It has deep roots in modern physics. Einstein's relativity will show us how time is relative to the observer, how it stretches and contracts. But even before diving into that odyssey, we must uproot the notion of a universal, absolute time. Imagine standing in a vast, featureless plain. How would you know you are moving? The same applies to time. Our perception of its flow depends intrinsically on the events occurring within it. If the universe were perfectly static, without any change at all, would time exist as we know it? The question is rhetorical, but its implication is monumental. Time is change. Time is motion. And if time is motion, then its nature is inherently relative. Mystics and ancient spiritual traditions intuited this long ago. In many Eastern philosophies, linear time is considered a construct of the mind. They spoke of a great now, an eternal present where past and future coexist. Though their methods were not empirical science, their vision often aligns with the most cutting-edge conclusions of quantum physics, where reality is far less solid and predictable than it appears. In that subatomic realm, time behaves in ways that defy everyday logic, opening doors to possibilities we are still struggling to understand. So the next time you look at a clock, do not think of an immutable flow. Think of a complex dance, a cosmic choreography where time is a dancer, not the stage. Think that your own consciousness is an active component in the experience of time. This is the first and most crucial revelation. Time, as we feel it, is a symphony created by the interaction of matter, energy, and perhaps the observer. It is an illusion, yes, but a powerful one that shapes our reality. And by understanding this illusion, we take the first step toward transcending it. Are you ready to dismantle even deeper the foundations of what you thought you knew about the universe? Perfect. Let us continue unraveling the mysteries of time. Prepare your minds, because now we enter the very fabric of space and time, a realm where gravity does not merely attract, but deforms reality itself. Remember the time dilation we mentioned, that phenomenon predicted by Einstein's special relativity, which states that time passes differently for observers in relative motion. The prediction was bold. The faster an object moves, the slower it experiences time compared to an observer at rest. To illustrate this idea, Einstein proposed a famous thought experiment, the twin paradox. Imagine two identical twins with their clocks synchronized down to the nanosecond. One of them, the traveler, boards a spaceship that accelerates to a speed close to that of light and makes a round trip to a distant star. The other twin, the sedentary one, stays on Earth. According to the theory, when the traveling twin returns to Earth, he will find that his sedentary twin has aged more than he has. His own clock will have recorded less time. He will have, in effect, traveled into his brother's future. For decades, this paradox sparked intense debates and misunderstandings. How could it be true? Aren't the laws of physics symmetrical? But the key lies in the asymmetry of the journey. The traveling twin experiences acceleration and deceleration, changing inertial frames, while the twin on Earth remains in a relatively constant frame of reference. This difference is fundamental. And the most astonishing thing is that this prediction did not remain confined to theory. It has been confirmed again and again with astonishing precision. Let me give you examples that do not come from science fiction novels, but from the most advanced laboratories and the vastness of space. Consider astronauts. Although they do not travel at near light speeds, they move much faster than we do on Earth. An astronaut aboard the International Space Station, orbiting Earth at about 28,000 km/h rate, experiences a very slight time dilation. After a year in space, an astronaut will have aged a fraction of a second less than if they had stayed on Earth. Yes, it is a tiny difference, almost imperceptible to our everyday perception, but it is a real, measurable difference. Cumulatively, if we spent centuries on a space station, the difference would be dramatic. The astronaut would literally be traveling into the future of their loved ones on Earth. But the clearest and most everyday example of time dilation that we already experience, and that is crucial to modern life, is the satellites of the Global Positioning System, the omnipresent GPS that guides our cars and phones. These satellites orbit the Earth at thousands of kilometers per hour and are also in a weaker gravitational field than the Earth's surface. Both conditions, high speed and lower gravity, affect the rate of their internal clocks. If these differences were not corrected, GPS systems would accumulate, positioning errors of about 10 kilometers per day. 10 kilometers in 24 hours. That would be disastrous for any application that relies on precision. Therefore, engineers must program satellite clocks to intentionally slow down before launch or apply constant corrections so that once in orbit, their ticking synchronizes with clocks on Earth's surface. This is irrefutable evidence, a tangible proof that time is not absolute, but relative, and that traveling into the future, even by milliseconds, is a daily reality dependent on Einsteinian physics. Time dilation is not limited to macroscopic objects like astronauts or satellites. It is also observed in the subatomic world. Take muons, for example. Muons are unstable particles created in the upper layers of Earth's atmosphere when cosmic rays collide with air atoms. They have a very short half-life of just 2.2 microseconds, that is, 2/millionths of a second. Without time dilation, most muons would decay before reaching the Earth's surface, even traveling at speeds close to that of light. Yet detectors on Earth record a significantly larger number of muons than classical physics would predict. Why? Because for muons, traveling at those extreme speeds, time passes more slowly. From their own perspective, their half-life is the same, but from our perspective on Earth, their internal clocks have slowed, allowing them to live long enough to reach the ground. They have, in effect, traveled a little further into the future of their own reference frame. These experiments, fellow observers, are the cosmic scars in the fabric of time that confirm Einstein's vision. We do not need elaborate science fiction time machines to witness that the future can be reached in subtle ways every time a plane takes off. Passengers flying at high speeds and at higher altitudes where gravity is slightly weaker age an infinitesimal fraction of a second, less than their loved ones on the ground. Time for them has dilated, extended. They have glimpsed, in the tiniest measure, a future they would not have reached if they had remained stationary. This understanding radically transforms our concept of time. It is no longer an inflexible constant that drags us along. It is a variable path, a dimension where speed and gravity act as regulators of our passage. If we can experience these small fractions of traveling into the future, what does it mean for grander possibilities? And if there were ways to manipulate these variables on much larger scales, to build bridges to distant eras? Time dilation is not the ultimate science fiction journey into the future, but its embryo, the irrefutable proof that time is an elastic canvas that can stretch and bend, opening the door to the true constructs of imagination. If time can be slowed or accelerated, it may one day be possible to stretch and fold it in such extreme ways that we could jump centuries or even millennia into the future. The implications are monumental and invite us to contemplate the theoretical tools physics has provided. Tools that, although they may now seem like a dream, could be the keys to constructing those cosmic bridges to unexpected destinations. Perfect. Our journey through space-time continues. Now fasten your seatbelts, because we will delve into the most exotic concepts of theoretical physics, those that promise shortcuts through the vastness of the cosmos. Chapter 4. Wormholes, cosmic bridges to unexpected destinations. Friends, explorers of the impossible, if time dilation has shown us that the future is, to some extent, accessible, the human mind, ever insatiable, cannot help but ask, what if we could jump not just seconds or minutes, but years, centuries, or even millennia? And what if there were cosmic shortcuts allowing us to cross vast stretches of space and time in the blink of an eye? This is where the most enigmatic and fascinating structures allowed by Einstein's general relativity come into play: wormholes. Imagine the universe not as a flat, rigid space, but as a sheet of paper. If you want to go from point A to point B on that sheet, the most obvious way is to draw a straight line between them. But what if you could fold the paper so that point A and point B touch? Then you could pierce a hole through both layers, creating an instant shortcut. This is the conceptual essence of a wormhole, also known as an Einstein-Rosen bridge, a theoretical solution to the equations of general relativity that describes a kind of tunnel connecting two distant points in space-time. The idea of wormholes first emerged in 1935, when Albert Einstein and Nathan Rosen explored the possibility that black holes, those gravitational singularities where space-time curves infinitely, might not be dead ends, but gateways to other regions of the universe, or even other universes. However, Einstein and Rosen's original wormholes were unstable and would collapse instantly if anything tried to pass through them, making them useless for travel. They were, in essence, throats that closed the moment you tried to enter. But the imagination of theoretical physicists, fueled by science fiction, did not stop there. In the 1980s, the renowned physicist Kip Thorne, seeking a way for characters in a Carl Sagan novel to travel through space, began investigating whether a wormhole could be traversable. His conclusion was astonishing. Theoretically, yes, but with a crucial condition. To keep a wormhole open and stable long enough for something to traverse it, an extremely exotic substance would be needed. Something with negative energy or exotic matter. What is this exotic matter or negative energy? It is not something we have encountered in our everyday universe. Ordinary matter, as you know, has positive energy and creates attractive gravity. But exotic matter would hypothetically have anti-gravitational properties, pushing space-time outward rather than pulling it inward. It would be like having beams that, instead of holding up a tunnel, push it outward, preventing it from collapsing. Without this substance, the wormhole would be a deadly trap, collapsing instantly. The existence of this exotic matter is one of the greatest challenges to the feasibility of wormholes. Although quantum physics allows negative energy fluctuations on subatomic scales, such as the Casimir effect, which we will explore later, the massive amount of negative energy required for a macroscopic traversable wormhole is far beyond our technological capabilities and perhaps beyond the nature of the universe itself. It's like asking for an ocean of antimatter when we can barely produce a few particles. Yet the fascination with wormholes persists for a fundamental reason: their potential for time travel. If a wormhole connects two distant points in space, it could also connect two distant points in time. The answer, according to general relativity, is dizzying. Theoretically, yes. If one end of a wormhole remained stationary while the other end moved at near light speed, experiencing time dilation, as we saw in the previous chapter, or was placed near a massive object like a black hole, the two ends of the tunnel would age at different rates. Upon returning the moving end, the two ends would no longer be synchronized in time. One entrance could lead to a distant future, while the other could lead to a distant past. Imagine the possibility. You enter one end in 2025 and exit the other in 2225. Even bolder, you enter in 2025 and exit in 1975. This is both the promise and the nightmare of wormholes as time machines. The ability to create closed time-like curves is what makes them so attractive to theorists, but also so problematic. The implications of such travel are profound and often paradoxical. If you could travel to the past, what would prevent you from altering events that would make you never exist or create irresolvable logical paradoxes? These are the questions that will lead us to the next chapters. Despite enormous theoretical and technological challenges, the existence of wormholes as mathematical solutions to Einstein's equations is a reminder of the astonishing flexibility of space-time. They force us to expand our minds beyond everyday experience and consider a universe where shortcuts are not only for space but also for time. They are a window, a realm of possibilities that defy our intuition, a hint that the universe is far stranger and more wonderful than our linear perception allows. Although traversable wormholes remain firmly in the realm of hypothesis and hard science fiction, their study pushes us to understand the limits and possibilities of physics. They compel us to confront the paradoxes that arise when time ceases to be a straight line and becomes a labyrinth of tunnels and shortcuts. But if wormholes offer a theoretical route to the past, what barriers does the universe impose to protect itself from the paradoxes such travel could create? The answer leads us to the dreaded event horizons and the profound implications of causality. Friends of knowledge, if wormholes have opened our minds to the dizzying possibility of shortcuts through space-time, the mere mention of traveling to the past instantly evokes a shadow, a logical shadow. A paradox so intricate it has tormented philosophers and physicists for generations, the dreaded grandfather paradox. Imagine for a moment that you, armed with the power to travel to the past, go back to a time before your parents were born and, for some reason, prevent your grandparents from meeting. If this happened, your parents would never be born, and by extension, neither would you. But if you were never born, how could you have traveled to the past to prevent your grandparents from meeting? Logic collapses. The universe implodes into an unbearable contradiction. This paradox is not a mere puzzle. It is a fundamental barrier that most theoretical physicists consider insurmountable for backward time travel. If the universe allowed such contradictions, the very structure of reality would crumble. How could a system exist if its own causes could be undone by its own effects? It's like trying to build a house while demolishing its foundation halfway through construction. Physics, in its tireless pursuit of coherence, has proposed various ways the universe might protect itself from these paradoxes. One of the most fascinating comes from the extreme properties of the most enigmatic objects in the cosmos: black holes. These cosmic colossi are the ultimate laboratory, where the laws of physics reach their limits, and at the heart of their mystery lies the concept of the event horizon. Imagine a black hole as a cosmic abyss. The event horizon is its point of no return, the theoretical surface beyond which nothing, not even light, can escape its immense gravitational pull. It is a one-way boundary. Everything that crosses this threshold plunges toward the central singularity. But what is truly astonishing is how this event horizon affects time. For an observer approaching a black hole's event horizon, time, from the perspective of a distant observer, seems to slow down progressively. The hands of their clock drag, their motion freezes, until at the horizon, time appears to stop entirely. This is gravitational time dilation at its most extreme. Physicists like Stephen Hawking speculated that event horizons might act as guardians of causality. If it were somehow possible to create a time machine that involved traveling to the past, such a machine would likely create its own event horizon, a space-time bubble preventing you from interacting with the past in a way that could create a paradox. You could observe the past, but not alter it. It would be like watching a movie without being able to change the script, a kind of cosmic censorship to preserve the universe's coherence. This idea is known as Stephen Hawking's chronology protection conjecture. It proposes that the laws of physics themselves conspire to prevent the appearance of closed time-like curves, hypothetical paths through space-time that would allow an object to return to its own past. In simpler terms, the universe has a sort of self-defense mechanism that prevents the grandfather paradox, a paradox that would challenge its own logical existence. Hawking, with his characteristic wit, even joked that the absence of tourists from the future is the best evidence against time travel. If it were possible and common, we would already be swarmed with visitors from the coming eras, curious to see how we live today. Beyond black holes, causality is a fundamental principle of our universe. It means that causes precede effects. An egg breaks after falling to the ground, not before. Time progresses in such a way that events have a logical sequence. If you could travel to the past and change an event, you would be creating an effect before its cause, or altering the cause of an effect that has already occurred. This is causal disorder, something traditional physics simply cannot allow without tearing the fabric of the universe. Some theorists have proposed alternative solutions to the grandfather paradox that do not require a total ban on time travel, but instead redefine how travel interacts with time. For example, the hypothesis of parallel universes, or many worlds, which we will explore in the next chapter, suggests that if you travel to the past and alter an event, you are not changing your own past. Instead, you are branching off a new timeline, creating a parallel universe where that alteration occurs. In this scenario, the paradox is resolved because you are not undoing your own existence, but creating a different branch of reality. Each decision, each intervention gives rise to a new version of the universe, a limitless garden of diverging paths. Another possibility is Novikov's self-consistency principle, which posits that if time travel to the past is possible, any attempt to change the past is destined to fail, or will result in an action that ironically helps the original event occur. The universe would self-correct. If you went back to prevent your grandparents from meeting, something would always intervene to ensure they did meet. Your very presence, your attempt to change the past, would in fact become part of the past itself. You would be an actor, not a rewriter. Ultimately, the event horizon and the paradoxes associated with time travel invite us to reflect on the fundamental nature of causality. Is it an unbreakable law of physics, defended with unprecedented ferocity by the universe, or a construct of our perception that can be transcended under extreme conditions or within the context of multiple realities? The absence of tourists from the future, the impossibility of building time machines that generate logical paradoxes, and the cosmic protection of the event horizon all suggest that the universe jealously guards its past, perhaps allowing us to look, but not touch. The truth is that although general relativity mathematically allows for the existence of backward time travel via closed time-like curves, such as those that could form around wormholes or infinitely rotating cylinders, most physicists believe that some law, yet to be discovered, or some insurmountable energy condition, prevents these phenomena from occurring in practice without violating fundamental principles of causality or requiring impossible amounts of energy. For now, the past remains a sealed book, readable perhaps through the flow of time, but unalterable by our hand. But what if that past, along with all possible futures, already exists in a realm of infinite possibilities? That is the door we are about to open. Friends of the cosmos, seekers of hidden truth, if the grandfather paradox has left us with the unsettling sense that time travel to the past is a dead end, a cosmic highway the universe refuses to open, what if the solution to these contradictions does not lie in prohibition, but in the unlimited expansion of reality itself? What if every decision we make, every event that occurs, is not a single path, but a branch in a garden of infinite paths, where all possibilities are realized in their own universe? Prepare yourselves, because we are about to delve into the astonishing and mind-bending hypothesis of parallel universes, a concept that redefines causality and destiny. The idea of parallel universes, or the many worlds interpretation of quantum mechanics, is one of the most radical and debated theories in modern physics. It was born from the need to solve one of the greatest mysteries of the quantum world: wave function collapse. Let me guide you through this paradox. In the subatomic realm, before being observed, particles do not exist in a defined state. An electron, for example, is neither here nor there. It exists in a superposition of all possible locations simultaneously. It is as if it were everywhere at once, a nebula of probabilities. But the moment we observe it, this superposition collapses and the electron appears in a defined location. This collapse has always been an enigma. What causes a particle to choose one of its infinite possibilities when observed? Is it the observer's consciousness, a fundamental interaction? Here is where Hugh Everett's many worlds interpretation from 1957 comes in. His solution is elegantly simple and terrifyingly complex at the same time. The wave function never collapses. Instead, at every instant a quantum measurement occurs. The universe splits or branches into multiple parallel universes. Imagine you have a coin in your hand and you toss it into the air. The coin is in a state of superposition. It is both heads and tails at once. According to the many worlds interpretation, the moment the coin lands and its outcome is revealed, say heads, the universe does not choose one result. In reality, the universe splits into two distinct branches. In one branch, the coin lands heads. In the other, completely separate and inaccessible branch, the coin lands tails, and you, the observer, also duplicate, experiencing reality in both branches simultaneously. It sounds crazy, right? But this theory solves the wave function collapse problem by postulating that all possible outcomes of every quantum event are equally real and occur in separate universes. Now let's apply this idea to time travel and the grandfather paradox. If you could travel to the past, say the 1950s, and accidentally or intentionally prevented your grandparents from meeting, the many worlds interpretation provides an elegant solution to the logical paradox. You're not altering your original timeline, because that timeline still exists in the universe you departed from. Instead, your action creates a new branch of the universe, a parallel universe where your grandparents never met, and therefore you were never born in that timeline. But the original timeline, where you were born and traveled from, remains intact. This means that every time a time traveler intervenes in the past, they are not rewriting history. They are creating a new future, a new branch of reality. Every possibility, no matter how small, becomes a real universe. If you hesitate between having coffee or tea, in one universe you drink coffee, in another tea. Every second, billions of branched universes sprout from ours, creating a multiverse of infinite possibilities, a garden of paths that endlessly diverge. The most astonishing implication is that in some parallel universe, every decision you could have made, no matter how insignificant, was made. In some universe, you chose a different career, married a different person, traveled to a distant place you never visited in this reality. Every regret, every what if, is a vibrant reality somewhere else in the multiverse. This not only resolves the grandfather paradox, but also invites a profound reflection on free will and destiny. Are we truly free if all our possible decisions already exist in some branch of the multiverse? Or is consciousness the mechanism that allows us to choose which branch to experience? Although the many worlds interpretation is mathematically consistent and avoids the logical paradoxes of wave function collapse, it is extremely difficult to test empirically. We have no known way to access or interact with these parallel universes. They remain ghostly entities, unobservable to us. Yet their conceptual elegance and ability to solve quantum problems keep them a viable and fascinating hypothesis for many physicists, who see in it a simpler explanation for the strange nature of quantum reality. Think of the universe as a gigantic, ever-growing tree, where each decision, each quantum fluctuation causes a new branch to extend. Our universe is just one leaf, a small part of an infinitely complex forest. This means that if wormholes could be opened and manipulated for backward time travel, causality would be preserved because it would not alter our past, but the past of a newly created branch. The time traveler is not a history rewriter, but a sower of new realities. Yet this idea, though liberating for temporal paradoxes, introduces other complexities. If there are infinite versions of ourselves, living all possible decisions, where does the true self reside? Is consciousness a bridge that crosses these branches, or are we anchored to a single timeline without realizing it? These are questions that take us beyond physics and into the realms of philosophy and neuroscience. The parallel universe hypothesis challenges us to redefine our own existence. We are not just the product of a single sequence of events, but the result of countless possibilities that have branched out. Each moment is a threshold, a crossroads where the universe expands, creating new realities with every blink of existence. It is an astonishing and humbling vision, reminding us of the unimaginable vastness and complexity of the cosmos. Although the technology to visit these parallel universes is currently beyond our comprehension, the mere existence of this theory forces us to confront the possibility that reality is not a single, solid truth, but a kaleidoscope of infinite possibilities, all equally real. The past, present, and future are not just a linear flow, but an intricate web of interconnected universes, where each decision is a cosmic event giving birth to new realities. And in that sense, time travel, though not rewriting what was, becomes the constant creation of what could be in an unlimited number of existences. Absolutely. Our immersion into the nature of time now brings us to one of the most fundamental and persistent questions we have asked. Why does time only move forward? Brace yourselves, observers, because we are about to confront the unbreakable law that seems to govern every moment of our existence. A law that tells us the past is immutable and the future a destiny. Chapter 7. The Arrow of Time. Why does time only move forward? Friends of mystery, travelers of the mind, if we have explored the elasticity of time according to Einstein, the possibility of wormholes and the dizzying idea of parallel universes, we still face a truth that, in its simplicity, is the most perplexing of all. In our everyday experience, time only moves forward. Broken eggs do not reassemble. Lit candles do not spontaneously extinguish. People age. They do not grow younger. Memory clings to the past. Anticipation projects into the future. We never remember the future, and we can never change what has already been. Why does time have such a stubborn direction, an unrelenting arrow that points only forward? This question takes us to the heart of one of the most fundamental and universal laws of the cosmos. The second law of thermodynamics. At its deepest essence, this law states that entropy, or the disorder of a closed system, always tends to increase over time. To understand it, imagine your room perfectly tidy. If you leave it alone without any external intervention, it will not become tidier. On the contrary, things will get messy, papers out of place, clothes scattered, dust accumulating. The universe as a whole is like that room, inexorably moving toward a state of greater disorder. Entropy is, in essence, a measure of disorder, randomness, or dispersed information. A system with low entropy is ordered and predictable. A system with high entropy is chaotic and uniform. Think of an ice cube in a glass of hot water. The cube, a state of low entropy with highly ordered water molecules, melts and mixes with the hotter water, spreading its energy and becoming part of a system with higher entropy. Water molecules in a more disordered and uniform state. This process is irreversible. You will never see hot water spontaneously freeze and separate into an ice cube without external energy being applied. The arrow of time, then, is the direction in which the universe's entropy increases. It is the direction in which things become disordered, break down, wear out, and mix together. Every event we observe in daily life, from burning wood to digesting food, is a process that increases the universe's total entropy. Energy disperses, information degrades, structures break down. This law is so fundamental that many physicists believe it is the true reason why time only moves forward. It's not that there's a time particle that can only move in one direction, but that the macroscopic state of the universe as a whole always evolves from less probable, ordered states to more probable, disordered states. And since the universe began in a state of extremely low entropy, the Big Bang, the only possible direction for entropy to increase is forward. But why was the Big Bang a state of such low entropy? This is one of the deepest, still unanswered questions in cosmology. Some suggest that our universe is just a bubble in a larger multiverse, and that its low entropy state is an anomaly, or simply how it began. Others propose cyclic universe theories where the universe expands, contracts, and perhaps a new Big Bang resets the entropic clock. However, for us inside this universe, the arrow of entropy is unbreakable. This arrow of time has profound implications for the possibility of traveling to the past. If going backward in time meant reversing entropy, undoing disorder, it would be fundamentally against the most powerful law of thermodynamics. Imagine going back in time to unbreak a plate. That would mean the plate's molecules, scattered and chaotic, spontaneously reassembling, decreasing entropy. In a closed system, this is statistically almost impossible. Physicists talk about multiple arrows of time: the thermodynamic arrow, the increase of entropy, the most fundamental; the cosmological arrow, the expansion of the universe. As the universe expands, its disorder also increases. The psychological arrow, our perception of time moving forward, remembering the past but not the future. This is deeply connected to the thermodynamic arrow. Our minds, like the universe, register change in the direction of increasing entropy. The radiation arrow, electromagnetic waves propagate outward, not inward, like ripples in a pond when a stone is thrown. All these arrows seem to point in the same direction, and the thermodynamic arrow, that of entropy, provides the deepest explanation of why we cannot travel backward in time the same way we can move forward in space. If time is, in a very real sense, the process of growing disorder, then going backward in time would mean going toward a state of lower disorder, which would require an injection of energy and a level of organization that seems to contradict the fundamental laws of nature on a large scale. But what does this mean for our understanding of the universe and our place in it? It means we are riding a wave of entropy, a wave that drags us inexorably forward. We cannot fight this cosmic tide. Our existence, the aging of our bodies, the evolution of stars, the decay of civilizations, all of it is a manifestation of the arrow of time, of the unstoppable rise of universal disorder. Yet, it is important to note that the fundamental laws of physics at the microscopic level, like Newton's laws or quantum mechanics, are mostly time-symmetric. This means that if you watched a video of subatomic particles colliding, you could not tell if the video was running forward or backward. Were it not for the fact that in the real world, microscopic systems tend to evolve from less probable to more probable states, the sheer number of particles and their interactions makes the increase of entropy overwhelmingly probable on a macroscopic scale, turning it into an unbreakable law. The arrow of time is the guardian of causality, the law ensuring the past remains immutable and that effects follow their causes. It anchors our reality, giving us a sense of before and after, of purpose and direction. Without the arrow of time, the universe would be a meaningless chaos, a soup of simultaneous, unconnected events. So next time you feel the passage of time, remember that you are experiencing one of the universe's deepest and most mysterious properties. You are being carried by the tide of entropy, a one-way journey that defines existence itself. While the speed of time may be relative, its direction for us, and for the cosmos, seems an unbreakable truth. But if time only moves forward, how has our imagination dreamed of defying it? The answer lies in human ingenuity and time machines. From fiction to theory. Absolutely. The flow of time drags us along, but the human imagination, that divine spark, has always dreamed of defying it. Prepare yourselves, observers, for we will leap from the pages of fantasy to the boldest frontiers of theoretical physics, exploring visions and concepts that could one day turn the dream of time travel into a possibility, however remote. Chapter 8. Time Machines. From fiction to quantum theory. Dreamers, seekers of the impossible, if the unbreakable arrow of time has anchored us firmly in the present, the human mind, with its insatiable thirst for exploration, has never accepted that limitation. Since the dawn of civilization, we have longed to undo past mistakes, to glimpse the future, to witness glorious or catastrophic eras. It is in this deep aspiration that time machines are born, a fantasy that has captivated generations and, surprisingly, is not entirely alien to the boldest frontiers of science. The archetypal image of a time machine comes, of course, from the visionary pen of H.G. Wells in his 1895 novel, The Time Machine. Wells presented a device of polished metal and quartz, a chair adorned with levers capable of sliding through time. For its era, it was a revolutionary idea, a break from the linear and absolute conception of time. His machine did not move through space, but through the fourth dimension, a concept that remarkably foreshadowed Einstein's future theories. Wells' machine was the physical embodiment of humanity's desire to transcend linearity, a symbol of our struggle against the relentless tick-tock of time. But beyond the brilliant imagination of novelists, what does science say? Is there any, however faint, basis for constructing a device that could allow us to travel through time? The answer is complex and branches into two paths: travel to the future and travel to the past. As we have already explored, travel to the future is already a reality confirmed by Einstein's special and general relativity. We do not need a complex machine of gears and flashing lights to move forward in time. We only need speed or extreme gravity. If we could build a spacecraft capable of traveling at a significant fraction of the speed of light, the passengers would experience time dilation dramatically. Imagine a ship traveling at 99.9% of light speed for only a few years for its crew. Upon returning to Earth, centuries or even millennia may have passed for humanity. They would have literally traveled to the future. This is not a hypothesis. It is a direct and tested consequence of the laws of physics as we know them. The technology to reach such speeds is beyond our current capabilities, but not a fundamental theoretical impossibility. The true chimera, the holy grail of time navigation, is travel to the past. Here, complexities and paradoxes multiply exponentially. However, the same general relativity of Einstein that gives us curved space-time also contains mathematical solutions that theoretically allow backward time travel. These solutions are known as closed time-like curves, or CTCs. What are these? They are hypothetical trajectories through space-time that end at the same point where they began. Not just spatially, but temporally. That is, an object or person could follow one of these paths and return to their own past. Various exotic configurations of matter and energy could theoretically create CTCs. Tipler cylinders. In 1974, physicist Frank Tipler demonstrated that an infinitely long, massive cylinder spinning at immense speed could create a space-time distortion extreme enough to generate CTCs. A spacecraft orbiting this cylinder could find itself traveling backward in time. The problem, of course, is the infinite length, immense mass, and energy required to spin it, a purely theoretical construct. Traversable wormholes. As we explored in Chapter 4, if a wormhole could be held open with exotic matter and one end accelerated to relativistic speeds or placed near a black hole, the traveling end would age more slowly, creating a time difference. Upon reconnecting with the stationary end, a CTC would form. Entering the end that aged slower, one could emerge at the faster aging end, arriving at a point in the past. This is the wormhole concept for time travel proposed by Kip Thorne and others. Warp bubbles, exotic drives. Some theoretical faster-than-light drives, like the Alcubierre metric, also imply CTCs, meaning superluminal travel is intrinsically linked to time travel. If you could travel faster than light, you could reach a destination before light, carrying the information of your departure. Quantum mechanics, that realm of the improbable, also offers speculative avenues. Quantum tunneling allows particles to cross energy barriers that would classically be insurmountable. Some theorists have wondered if analogous phenomena could allow subatomic temporal jumps, though macroscopic implications are even more remote. Loop quantum gravity, or string theory, may one day shed light on space-time at fundamental scales, potentially revealing whether CTCs are real features of the universe or merely mathematical curiosities cancelled in a complete theory. Yet, despite these fascinating theoretical possibilities, there are monumental barriers to building a real-time machine. The first is energy. The amount needed to warp space-time as required is so vast, it exceeds the capabilities of our civilization, equivalent to entire stars. The second is exotic matter or negative energy, needed to hold wormholes open or create Tipler cylinders. We have no evidence it exists in the required amounts, and if it does, it is likely only at ephemeral quantum scales. The third is logical paradoxes, which many physicists believe some yet undiscovered law would forbid to prevent contradictions. Hawking's chronology, protection conjecture, is one such proposal. Still, the mere idea that general relativity, a theory of astonishing precision describing the universe, contains these time travel solutions is itself a revelation. It tells us that time is not what we thought, that it is far more than a simple line. It is a fabric, a field, a dimension that could, in principle, be manipulated. We are not talking about going back to kill Hitler or steal books from the Library of Alexandria. We are talking about universe-bending deformations so extreme they defy our understanding of reality and causality. Time machines, for now, belong to the realm of science fiction, but serve as a beacon for theoretical physicists, forcing us to push the limits of our knowledge, explore every corner of Einstein's equations, and seek the deepest truths about the nature of space, time, and existence. They remind us that the universe is a place of limitless wonder, where what is fantasy today could become the next chapter in humanity's relentless quest for knowledge. And in that quest, perhaps one day, we will unlock the secrets to bending not only space, but time itself. Absolutely. Our journey through the mysteries of time now takes us to an even more fundamental scale, to the theoretical threads that, according to some of the most cutting-edge theories, could be the sutures of the universe and perhaps the keys to manipulating time itself. Get ready, observers, because we are about to venture into the realm of cosmic speculation, where microscopic defects in the fabric of space-time could conceal the most unexpected routes to the past. Chapter 9. Cosmic Strings. The universe's threads with temporal potential. Curious friends, explorers of the cosmic fabric. So far, we have discussed how mass and energy can curve space-time and how hypothetical machines or wormholes could theoretically exploit those curvatures for time travel. But what if there were objects in the universe, relics from the very Big Bang, that already had the inherent ability to warp time in ways that open doors to the past. Here is where theoretical physics presents one of its most exotic and fascinating concepts: cosmic strings. Imagine that the universe in its earliest moments was not a smooth, uniform space, but a bubbling soup of energy and fields cooling rapidly. In that process, just as defects form in a cooling crystal or cracks appear in ice, imperfections could have formed in the very fabric of space-time. These imperfections are what we call cosmic strings. They are not the tiny strings of string theory, which are much smaller and fundamental units of matter, but macroscopic objects, extraordinarily dense, thin one-dimensional faults stretching for billions of light years across the cosmos. Think of the universe as a vast silk quilt, and these cosmic strings as incredibly fine but dense, rigid threads running through it, tightening and deforming it as they go. If cosmic strings exist, they are relics of a primordial era, when the universe was so young and hot that the fundamental forces of nature were unified. Their separation and freezing into what we know today may have left behind these lines of high energy and density. What makes cosmic strings so astonishing and relevant to our temporal journey is their incredible density. A cosmic string no wider than a proton could weigh more than the entire Earth for every meter of its length. Such extreme density has drastic gravitational consequences. According to Einstein's general relativity, a cosmic string would not curve space-time like a star or a black hole. Instead of curving it into a depression, a cosmic string would warp space in a very particular way, creating a kind of cone. Imagine a sheet of paper. If you remove a small wedge and tape the edges together, you get a cone. You have created a space that, while locally flat, has an angular deficit. A cosmic string would do something similar to space-time. If you traveled around a cosmic string, you would find that completing a full orbit takes you through an angle less than 360 degrees. The space behind the string is slightly deformed with an angular gap. And here is where the magic, or rather extreme physics, begins to hint at the possibility of time travel. In the 1980s, physicist J. Richard Gott, building on the work of others, demonstrated that if two parallel cosmic strings moved relative to each other at near light speed, or if a single cosmic string formed a closed loop and moved rapidly, they could generate the famous closed time-like curves, CTCs. To understand how, think again of the elastic fabric of space-time. So, if you have two very massive cosmic strings moving extremely fast next to each other, the distortions each creates in space-time could interact in such a way that they form a temporal shortcut. A spacecraft moving around these two strings at the right speed and direction could find itself back in its own past. It would be as if the strings twisted the fabric of time, forming a knot that allows a backward leap. This concept is astonishing because, unlike wormholes which require hypothetical exotic matter, cosmic strings are relics of the grand unification of forces at the universe's beginning and could have formed naturally. However, there are significant challenges. First, observational evidence for cosmic strings is very scarce. Although scientists have searched, for instance, for their potential gravitational effects on the cosmic microwave background or galaxy formation, no conclusive proof exists. Second, even if cosmic strings existed, the conditions necessary to form CTCs and allow time travel are incredibly difficult. Strings would have to be extremely long and straight, or form loops with precise geometry. They would have to move at speeds near that of light, which is already a huge technological challenge. The energy required to move or stabilize such configurations is beyond anything we can conceive. And of course, there is the problem of paradoxes. If cosmic strings truly created CTCs, how would the grandfather paradox resolve? Many worlds' interpretation could come into play, where each trip to the past creates a new timeline, or Hawking's chronology protection conjecture could prevent the stable formation of such CTCs. Physics is still debating these fundamental questions, and the existence of a natural time machine in the universe remains a major unknown. The beauty of cosmic strings, however, lies in their potential to unify aspects of physics. If they exist, they would be a bridge between particle physics, because of their origin in early universe phase transitions, and cosmology, because of their scale and gravitational effects. And if they also have the potential to bend time, they add another layer of wonder to their already fascinating nature. These primordial threads of the universe, if real, suggest that space-time is not just a passive canvas, but an active fabric that can be twisted and deformed by exotic objects in unexpected ways. They invite us to imagine a cosmos where relics of its own infancy could be keys to unlocking the doors of time. They remind us that the laws of physics, though rigorous, may have solutions that defy our intuition and open our minds to possibilities we have yet to fully comprehend. So next time you look at the night sky, beyond the stars, remember that theories suggest the universe may be threaded with invisible strands of inconceivable density, relics of its birth, which in their cosmic dance may have the power to bend time upon itself, creating shortcuts that challenge the very linearity of our existence. But if these journeys to the past are theoretically possible, the question remains: how does the universe handle the inevitable paradoxes? It is to this logical crossroads that we now turn. Absolutely. Our journey through the realms of time has led us along astonishing paths, from Einsteinian flexibility to cosmic strings. But now we face the thorniest question of all, the Gordian knot that threatens to unravel all temporal logic. Get ready, observers, because we are about to dive into the abyss of paradoxes, those intricate dead ends where the future violently collides with the past, challenging the very coherence of reality. Chapter 10. Time Traveler Paradoxes, when the future collides with the past. Friends of the enigma, weavers of realities, if we have dreamed of sliding our minds through the threads of time, the mere idea of traveling to the past invokes a legion of logical demons, ghosts of contradictions lurking in every corner of the chronal continuum. We are not talking about mere puzzles, but existential abysses which, if unresolved, make the very notion of altering the past a categorical impossibility. Prepare to confront the time traveler paradoxes, the insurmountable walls the universe may have erected to protect itself. The most famous, haunting every debate about traveling to the past, is the grandfather paradox. We mentioned it briefly before. If a traveler goes back in time and somehow prevents the birth of one of their parents or grandparents, then the traveler themselves would never exist. But if they never existed, how could they have traveled back in time in the first place? It is an unbreakable causal loop, an absurd tautology. If the cause, the time travel, annuls the effect, the traveler's existence, the reality collapses. It's as if a song erased itself while being sung. Logic, at this point, screams. But the grandfather paradox is just the tip of the iceberg. There are others, equally unsettling, arising when the future collides with the past. The self-consistency or closed causal loop paradox does not negate the traveler's existence, but creates a cycle of events where a future event causes a past event, which in turn causes the future event. Imagine a traveler who goes back in time to teach a young scientist the plans for a time machine that the traveler themselves invented. The young scientist uses those plans to build the machine, grows up, and travels back to teach their younger self the same plans. Who invented the time machine? There is no original point. The information or object exists without being created. It is a loop without beginning or end, an infinity of cause and effect without an initial spark. It is like a musical score performed but never composed. The bootstrap or ontological paradox is closely linked to self-consistency. This paradox centers on the creation of information or an object out of nothing through a temporal loop. The classic example is a time traveler who goes back carrying a book with all of Shakespeare's works. They meet the young Shakespeare and give him the book. The young Shakespeare copies the works, publishes them, and becomes the famous playwright. Years later, the traveler takes a copy of Shakespeare's works and brings it back to give to their younger self. Who wrote Shakespeare's works? No one originally. They simply exist in a temporal loop with no point of origin. The information, the works, creates itself. It is self-reference without a starting point, a paradox of existence itself. These paradoxes are not mere intellectual curiosities. They are profound objections to the possibility of traveling to the past and altering it. If the universe is a coherent system, how could it allow such contradictions? Most theoretical physicists contemplating time travel must find a way to resolve these paradoxes or conclude that backward time travel is essentially impossible. Several proposals address these contradictions, some of which we have already touched upon. Hawking's chronology. Protection conjecture. This postulates that some fundamental law of physics, not yet fully understood, will prevent the conditions necessary for backward time travel that would generate paradoxes. The universe protects itself like a cosmic antibody against inconsistency. The laws of physics will not allow a time machine to create a logical contradiction. If you tried to kill your grandfather, something would always prevent it. Your weapon would jam. An inexplicable force would stop you. Fate, in this scenario, is unbreakable. Not because it is predetermined, but because any attempt to change it ironically becomes part of how it unfolds. Novikov's self-consistency principle. This principle suggests that if time travel to the past is possible, only those journeys that do not alter the past in a paradoxical way are allowed. Any action you attempt to change the past will result in something that aligns with original events, or even facilitates them. You cannot change the past because you have already been part of it. Your time travel journey and any actions you take are already written into history and consistent with events as they unfolded. For example, if you traveled back to stop a fire, you might actually be the person who accidentally caused it while trying to prevent it, or your intervention would be so insignificant that the fire occurs anyway. You are an actor in the play, not the playwright. Many worlds interpretation, Hugh Everett. Perhaps the most radical yet elegantly simple solution. If you travel to the past and kill your grandfather, you do not erase your own existence. Instead, at the moment of your intervention, the universe splits into two distinct branches. In the branch you came from, your grandparents met and you were born. In the new branch you have created, your grandparents did not meet, and you do not exist in that reality. There is no paradox, because all possibilities are realized in parallel universes. Each act of intervention creates a new timeline, a new universe. The very existence of these paradoxes forces us to contemplate the deep interconnectedness of cause and effect, past and future. They show us that time is not a mere backdrop against which we act, but an active element, a guardian of its own consistency. If unrestricted travel to the past were possible, the universe would descend into logical chaos, a collection of meaningless contradictions. The absence of evidence for time travel, the lack of tourists from the future, and the robustness of causality in our macroscopic experience all point to one conclusion. Either traveling to the past is impossible, or it is so intrinsically constrained by physical laws and paradoxes that it nullifies itself. However, studying these paradoxes is far from a futile exercise. It allows us to understand the limits of what the laws of physics permit and pushes us to seek more complete theories that might unify gravity, which allows CTCs with quantum mechanics, which could offer solutions or new constraints. It forces us to question the very nature of destiny, free will, and reality. Are we condemned to an unchangeable future, or are we agents within a matrix of infinite possibilities? The answers to these paradoxes offer a window into the fundamental structure of the universe. By confronting them, we take one step closer to understanding not only time, but also the complexity and wonder of existence. Friends of the cosmic order, seekers of harmony within apparent chaos, if the grandfather and bootstrap paradoxes have left us uneasy about a universe that seems logically unstable in the face of time travel, theoretical physics offers a perspective that, without denying the possibility of moving through time, ensures causal coherence remains intact. We speak of Novikov's self-consistency principle, a profound idea proposing that if time travel is possible, any event a traveler attempts to alter in the past is destined to be consistent with history as it already occurred. The universe, in essence, will not allow paradoxes to form. To understand the core of this principle, formulated by Russian physicist Igor Novikov in the 1980s, imagine space-time as a massive, complex puzzle. Every piece represents an event, an action, an interaction. Novikov's self-consistency principle suggests that if you insert a new piece, your journey to the past and any actions you take, this piece must already fit perfectly with all the others. You cannot force it into a place where it contradicts the pieces that already exist. Let's revisit the grandfather paradox. According to Novikov, if a traveler goes back in time intending to prevent their grandparents from meeting, their attempt will always, without exception, fail. It's not that linear time is unbreakable or that past travel is impossible, but that any time loop formed must be self-consistent. This means that if an event is caused by a future event, that future event must indeed occur. Here's a clearer example. Imagine a time traveler going back to prevent a building from burning in a catastrophic fire. They arrive in the past and try to stop it, but through a twist of fate, their intervention either contributes to or fails to prevent the fire exactly as it originally happened. Perhaps in trying to extinguish a small spark, they accidentally spill fuel, intensifying the flames, or maybe their presence distracts someone who might have stopped the fire. In this scenario, the traveler does not change the past. They become an integral part of it. Their attempt to alter the event ironically ensures that the event occurs. History is not rewritten, it is reinforced. This principle is deeply deterministic in nature. It suggests that if time travel to the past is possible, we do not have free will to change history. The actions of a time traveler are already written into the fabric of space-time. Every event in the time loop is both the cause and effect of the other events within that loop. There is no original starting point for causes, as all causes influence one another within the loop. Novikov argues that if the laws of physics permit closed time-like curves, CTCs, then events occurring within those CTCs must be consistent with events outside of them. Contradictions cannot exist. History is fixed, and the time traveler is not an agent of change, but a cog in the mechanism of destiny. Their existence in the past has already happened, and any actions they take there are already part of history. Consider the example of Shakespeare's book in the bootstrap paradox. If a time traveler takes Shakespeare's book to the past and gives it to the young Shakespeare, and that becomes the origin of Shakespeare's works, Novikov's principle asserts that the loop is self-consistent. There is no first copy of the book. The book and its content have always existed within that closed temporal loop. Information is not created from nothing. It simply exists as part of the structure of space-time, perpetuating itself. This principle appeals to many physicists because it avoids repugnant logical paradoxes without completely forbidding time travel. It allows the mathematics of general relativity, which predicts CTCs, to coexist with the necessity of a causally coherent universe. There are no paradoxes because any event that can occur in the past must occur in a way consistent with already established history. However, Novikov's self-consistency principle also has its critics and profound philosophical implications. If everything we do in a time travel scenario is predetermined and nothing can be changed, where does free will remain? If our attempts to alter the past become part of the unchangeable past, we are mere puppets in a universe that already has its script written. This echoes ancient debates about fate and predestination. Moreover, if the universe protects itself in this way, how does it do so? Is there some subtle force diverting our attempts? Or are the laws of probability so overwhelming that any effort to create a paradox has an infinitesimally small chance of success, tending to zero? Some theorists suggest that even at the quantum level, the probabilities of a paradoxical event would automatically cancel, ensuring coherence. Despite its deterministic implications, Novikov's principle offers a vision of a universe where time, though malleable, is inherently robust and consistent. It does not allow reality to tear itself apart through contradictions. It invites us to think of history not as a sequence of events that could have been different, but as a tapestry where every thread, even that of a time traveler, was already in place. The pursuit of self-consistency is a powerful force in physics, telling us that the universe has a way of holding itself together even in the face of the most dizzying possibilities. If CTCs are a real feature of our universe, Novikov's self-consistency principle could act as the cosmic traffic rule, ensuring that the flow of time, even when it bends upon itself, never becomes a chaotic traffic jam. It provides an elegant answer to the grandfather paradox, though for some it is slightly discouraging, as it limits our agency in the past, while reassuring us that the universe we inhabit is fundamentally logical and coherent. Intrepid friends, dreamers of the past and future, if science has opened the door to the theoretical possibility of time travel, even at minute scales, it is crucial not to be carried away by mere awe. With every advance in understanding these phenomena, questions of overwhelming ethical and practical depth emerge. If we could go back, even for an instant, what dangers would lurk? What responsibilities would we bear? This is where the concept of the butterfly effect looms, a reminder of the unbreakable interconnectedness of all that exists. The butterfly effect comes from chaos theory, a field of mathematics and physics studying dynamic systems extremely sensitive to initial conditions. Its name was coined by meteorologist Edward Lorenz in the 1960s, when he discovered that a minuscule change in his climate model, like a butterfly flapping its wings in Brazil, could theoretically trigger a tornado in Texas weeks later. The analogy is simple yet powerful. A small disturbance in a complex system can amplify exponentially over time, leading to massively different and unpredictable outcomes. Now imagine applying this idea to time travel. If a chrononaut, a time traveler, returns to the past, even the most trivial action, the slightest whisper, or the accidental brushing of a leaf could have catastrophic ramifications. A fly crushed in the Cretaceous could alter the evolutionary chain so that dinosaurs never went extinct or humans never appeared. A simple remark to someone in the 17th century could change their life path, which in turn affects thousands of others, altering the course of history in unimaginable ways. Think about it. Every moment in time results from an infinity of causes and effects. Our present is the culmination of billions of interactions, decisions, accidents, and causal chains. Altering even a single one of those causes, however minor, could trigger a cascade of events diverging from the original history. If time is a river, the butterfly effect tells us that even a small stone tossed into its source can redirect its course thousands of kilometers downstream. This presents monumental ethical and practical challenges for any hypothetical time traveler. Absolute unpredictability, even with knowledge of the laws of physics. The complexity of a system like human history is so vast that predicting the consequences of the smallest alteration would be impossible. What might seem a benign intervention could lead to unimaginable catastrophe. How does one measure the success of a temporal mission if every action could have unintended large-scale consequences? The responsibility is incalculable. A chrononaut returning to the past would bear the weight of every possible alteration. Who decides what is a good or bad change? Who pays the price for a radically different history? Intervention becomes an act of playing God, with results even a deity could not predict. The moral paradox. If time travel were possible, the temptation to fix historical mistakes, prevent wars or disasters, would be overwhelming. Yet each fix could introduce new, worse problems, creating a future no one could have foreseen. The pursuit of historical perfection could lead to even greater chaos. The butterfly effect is one reason many time travel theories, especially those involving altering the past, resort to solutions like Novikov's self-consistency principle or the many worlds interpretation. If the universe protects itself, Novikov, or each intervention spawns a new timeline, many worlds, you're not altering your original history, but creating a new one, avoiding direct paradoxes. Yet even in a many worlds framework, a chrononaut jumping to a new branch creates a reality where things are different and that action carries existential consequences. The delicacy of fate remains, now manifesting as the creation of countless alternative realities. Consider it personally. Every decision you have made shaped your present. What if you could go back and change a crucial choice? Would you still exist as the person you are, or would your current self vanish, replaced by an alternate version of you? The butterfly effect reminds us that we are the product of an incredibly intricate causal chain. Untying that knot is an act of cosmic irresponsibility. Hence, the idea of the chrononaut, the brave or reckless time explorer, comes with a profound warning. Space-time is not a blank canvas for us to paint at will. It is a living tapestry, interconnected and highly sensitive, where every thread, every knot, every fiber is entwined with the others in ways we are only beginning to understand. A single flap in the past could rewrite not only history, but the universe itself. Yes, while wormholes and mathematical solutions invite us to dream of time travel, the butterfly effect implores caution. It forces us to consider not just whether we can travel through centuries, but whether we should, and at what cost. It reminds us that fate, whether unchangeable or a collection of infinite branches, is a fabric so delicate that any attempt to manipulate it could have consequences beyond our comprehension, altering the cosmic symphony in unimaginable ways. Friends of inner mystery, explorers of the psyche, if physics has revealed that time is not an inflexible constant, but an elastic dimension shaped by the dance of matter and energy, the inevitable question arises: how does our own consciousness interact with this malleable reality? Is the time we experience, the relentless march of hours, an objective truth of the cosmos, or a subjective construction orchestrated by the complex, mysterious universe residing within our own mind? Think about your own experiences. You've lived moments where time seemed to slow down almost to a halt. An impending car accident, a moment of epiphany, or extreme danger. Every second stretches, every detail is etched with terrifying clarity. And you've also experienced moments where time seemed to fly. Wonderful vacations, a day of intense focus, the end of a deep conversation, hours that feel like minutes. This variability, this elasticity of our temporal experience, is not an illusion. It is a profound truth about how our mind processes the flow of existence. Psychology and neuroscience have explored this subjective perception of time in great detail. They've discovered that factors like emotion, attention, age, and even certain substances can drastically alter how we experience the passage of seconds and minutes. When we're bored or stressed, time seems to drag. When we're immersed in a pleasurable or challenging activity, time flies. This suggests that the clock in our head is not as mechanical and constant as a universal stopwatch. But what does this mean in the context of the physics of time? Einstein's general relativity describes time as a coordinate in space-time, a physical dimension. Yet our phenomenological experience of time, the sense of a moving present and a fading past, is something that physics alone does not fully explain. This is where consciousness comes in. Some theorists exploring the boundaries between neuroscience, philosophy, and quantum physics have proposed bold ideas. What if consciousness were not just a product of the brain, but a fundamental property of the universe, perhaps even the factor that selects or perceives one of the infinite possibilities that exist in the block universe or multiverse? Yes, as the many worlds interpretation suggests, all possible realities already exist. Our consciousness may be the beam of light that illuminates one of these branches, creating the experience of linear time. The brain, as you know, has no single time center. Instead, time perception is a complex function distributed across several brain regions that integrate sensory information, memory, attention, and emotion. How our brain sequences events and binds moments into a coherent narrative is what creates our experience of duration and temporal flow. Every neuron firing, every synapse forming, part of this complex dance that gives us our sense of the hour. Scientists like neuroscientist David Eagleman have studied how our perception of time changes in extreme situations, moments of imminent danger, when the brain floods the system with adrenaline. The amygdala, a key region for emotion and memory, seems to record an unusually large amount of sensory information. More information per perceived unit of time creates the sensation that time is slowing down. When recalling the event, the abundance of detailed memories makes it feel as though it lasted longer. The universe hasn't slowed down. Our brain processor has sped up. But the connection between consciousness and time goes beyond mere subjective perception. In quantum physics, the observer's consciousness has been a controversial topic since the beginning. The famous Schrödinger's cat paradox, or the double-slit experiment, suggests that observation or measurement of a quantum system forces it from a superposition of multiple states into a defined state. While most physicists attribute wave function collapse to interaction with the macroscopic environment, not necessarily consciousness. Some philosophers and theorists have explored the idea that consciousness may play a more active role in creating the reality we observe, and by extension, our experience of time. If our consciousness has a role in observing and defining reality at a fundamental level, it could also be a key to unlocking other temporal dimensions or experiencing time in ways that transcend our linear perception. This is bold speculation, but not without philosophical grounding. Many spiritual and mystical traditions have long maintained that true time is cyclical, not linear, or that eternity is a great now experienced in higher states of consciousness. Think about it. In dreams, time often behaves illogically. A 5-minute dream can feel like hours or even days. In deep meditation or under psychedelics, some report timelessness, a connection with past or future, or a simultaneous perception of events. While these are subjective experiences, not scientific proof of time travel, they suggest our brain's programming for linear time is flexible and can be altered by states of consciousness. In a very real sense, we control our timing. Yes, our experience of the passage of time is shaped by attention, emotion, age, and how the brain processes information. But on a deeper level, could consciousness be the mechanism that lets us navigate the vast, fixed block of space-time or the infinite branches of the multiverse, creating the illusion of flowing time? This is one of the most exciting and least understood frontiers of science, the meeting point of physics, neuroscience, and philosophy. It invites us to explore not only the external universe, but the internal universe of our own mind and consciousness. Perhaps the key to understanding time and even transcending it is not in a colossal machine, but in the subtle, profound machinery of our own conscious existence. Understanding consciousness, that mystery within each of us, leads us to explore experiences that seem to defy the laws of physics. Explorers of the inner realms, navigators of the night, if consciousness is a crucial actor in orchestrating our experience of time, what happens when the bonds of physical reality loosen? When the mind frees itself from ordinary perception? It is in those liminal moments, within the lyrical tapestry of dreams, altered states of consciousness, and at the thresholds of death, where time seems to dance to an entirely different rhythm, suggesting temporal dimensions beyond our waking comprehension. Consider the most common and enigmatic experience: sleep. How many times have you lived a dream sequence that felt like hours or days, only to wake and realize mere minutes have passed in the real world? This phenomenon, where time perception stretches and compresses in astonishing ways, testifies to the malleability of time within the laboratory of the mind. In REM sleep, especially lucid dreaming, where you are aware of dreaming and can even control the dream's content, the brain can construct complex, extended narratives in surprisingly short, objective time. It's as if, in the dream world, consciousness is freed from the linear tick-tock, allowing us to compress or expand duration at will, a form of internal time dilation. Dreams go beyond compression. Throughout history, countless cultures have attributed dreams with glimpses of the future or revelations of the past. From biblical prophetic dreams to shamanic visions, the idea that dreams transcend temporal barriers has persisted. Modern science often explains this through memory consolidation, emotional processing, or unconscious desire. Yet the persistence of these experiences invites reflection. Could it be that by disconnecting from sensory perception of the physical world, consciousness accesses a deeper layer of space-time, where distinctions between past, present, and future are less rigid, as a block universe would suggest? Beyond dreams, there are altered states of consciousness induced by deep meditation, hypnosis, or certain psychedelic substances. Individuals under these influences often report timelessness, a sense that time ceases entirely, or merging with an eternal present where all exists simultaneously. Others describe vivid regressions to past lives or forgotten moments of childhood. While science attributes this to neural reorganization and neurotransmitter release, the subjective experience is a mind navigating the continuous chronos without constraint. Then there are near-death experiences, accounts of people on the brink of clinical death who return with extraordinary narratives. A significant percentage report experiencing their entire life in an instant. A panorama where every memory and moment is experienced simultaneously, as if their entire existence were compressed into a single eternal now. Some also describe visions of future events or encounters with deceased loved ones, breaking temporal and spatial barriers. Why science seeks explanations in cerebral processes like oxygen deprivation or endorphin release, for those experiencing it, these events are encounters with a reality that defies the physics we know. What do these experiences tell us about time and our capacity to transcend it? They suggest several possibilities. Time as a cognitive construct. If the brain can manipulate time so drastically in altered states, it reinforces the idea that our linear perception of time is largely a construction of our own mind. Our internal biological clock, influenced by attention and emotion, is a subjective regulator. Access to higher dimensions. Could consciousness, in these states, tune into dimensions of space-time normally beyond reach? If the universe is a four-dimensional block where past, present, and future coexist, perhaps in expanded states of consciousness, we perceive more of this block, though fragmented or symbolically. Consciousness as a fundamental observer. If consciousness plays a role in wave function collapse or selecting realities, as suggested in quantum mechanics, then in altered states this observational ability may be amplified, letting us perceive temporal patterns or causal connections otherwise invisible. Memory and anticipation differently. Perhaps instead of literal time travel, these experiences are extreme forms of memory processing. Recalling the past hyper-realistically and anticipating the future based on complex patterns. Yet the vivid sense of being there challenges purely cerebral explanations. Science is still in the early stages of understanding the complex interaction between consciousness, the brain, and time. Yet these subjective experiences, resonating across cultures and eras, open a window to the possibility that our perception of time is far more malleable and profound than we believe. They invite us to question whether the reality we experience in waking life is the only truth. Exploring these internal mysteries reveals that the study of time is not confined to the vast cosmos or intricate mathematical models. It also resides in the uncharted universe of our own mind. Perhaps the key to understanding the deepest truths of time does not lie in a titanic machine or gravitational singularity, but in the subtle, enigmatic capacity of our own consciousness to dance with the rhythm of the universe. A rhythm that sometimes allows us to glimpse the past or future, even in the silent theater of our dreams. And this dance brings us back to the foundational pillars that allowed us to even conceive of these ideas. The unshakable theories of Einstein. Friends of knowledge, engineers of reality in your minds, if we have explored the frontiers of time, from paradoxes to the most ethereal experiences of consciousness, it is vital that we anchor our understanding in the solid foundations of modern physics. Every concept, every possibility of temporal travel we've discussed originates from the brilliant mind of Albert Einstein and his two monumental theories of relativity, special and general. They are not just theories, they are the cosmic map that allowed us to even conceive of the malleability of time. Let's go back to 1905. A young, unknown Albert Einstein publishes his theory of special relativity. This marked a before and after in the history of physics, a revolution that toppled centuries of Newtonian thought. What was its central premise? Two postulates that, in their apparent simplicity, would change the universe forever. The principle of relativity. The laws of physics are the same for all observers, moving at constant speed in a straight line in inertial frames. Imagine being in a spaceship moving at constant speed in deep space. There is no way to tell if you are moving or at rest without an external reference. The constancy of the speed of light. The speed of light in a vacuum is the same for all observers, regardless of the speed of the source or the observer. This is the most counterintuitive and revolutionary postulate. Think of a car throwing a ball. If the car moves at 50 km/h and throws the ball at 10 km/h, an outside observer sees the ball move at 60 km/h. But with light, it doesn't work that way. If a spaceship moves at 90% the speed of light and emits a beam forward, the light doesn't travel at 90% plus the speed of light. It still moves at the speed of light for all observers. The consequences of these two principles are astonishing and direct. Time dilation. If the speed of light is constant for everyone and you move faster, time must slow down for you relative to a stationary observer. This is time dilation, which we've already discussed with astronauts and muons. It's not an optical illusion, it's a physical reality. Their personal clocks, metabolism, aging, everything slows down. You are, in fact, traveling into the future of the slower observer. Length contraction. Objects moving at speeds close to light shrink along the direction of motion from the perspective of a stationary observer. Relativistic mass increase. The mass of an object rises as it approaches the speed of light. Mass-energy equivalence, EMC2. Mass and energy are not separate entities. They are two forms of the same thing. A tiny amount of mass can convert into an enormous amount of energy and vice versa. This is the most famous equation in history and also a direct consequence of special relativity. Special relativity revealed that time is not absolute, but relative to the observer's motion. But Einstein's genius didn't stop there. He spent another 10 years until 1915 developing his masterpiece, general relativity. Here, he not only incorporated acceleration, but fused space, time, and gravity into a single, monumental structure. What was the great revelation of general relativity? Gravity is not a force as Newton had conceived. Gravity is actually the manifestation of the curvature of space-time caused by the presence of mass and energy. Imagine the elastic sheet again. A bowling ball deforms it. A smaller object moving nearby is not pulled by an invisible force. It simply follows the curvature of the sheet. The Earth is not pulled by the Sun. The Earth follows the curvature of space-time created by the Sun's mass. The consequences of general relativity for time are even deeper. Gravitational time dilation, the stronger the gravitational field, the slower time passes. We discussed this with GPS and black holes. A clock on Earth's surface ticks slightly slower than a clock in space, away from Earth's gravitational influence. A clock at the edge of a black hole would appear to stop for a distant observer. Gravity itself becomes a shaper of time. Black holes. General relativity predicted the existence of these singularities where space-time curves infinitely, and nothing, not even light, can escape. Gravitational waves. Ripples in the fabric of space-time that travel at light speed, predicted by Einstein and detected a century later. These waves are like ripples in a pond when you throw a stone, but they are waves in the very structure of reality. These two theories form the unshakable foundations that opened the door to the theoretical possibility of time travel. Time dilation by speed and gravity is proof that we are already traveling into the future, albeit on a tiny scale. And the malleability of space-time, its ability to bend and warp, is what allows exotic mathematical solutions like wormholes or Tipler cylinders to exist on paper, offering, at least theoretically, routes for large-scale travel and even the intriguing and problematic closed time-like curves, CTCs, that could take us to the past. Without Einstein's relativity, time travel would remain pure fantasy, with no grounding in the physical universe. He provided the mathematical and conceptual framework to understand that time is not a fixed constant, but an elastic, dynamic dimension, intrinsically linked to space, mass, and energy. His work not only allowed us to measure the universe with unprecedented precision, but also gave us the tools to dream of manipulating it in ways previously unimaginable. Relativity is the language in which the universe speaks to us about its deep structure, and that language tells us that time is a fabric that can be stretched, compressed, and, even under extreme and theoretical conditions, folded upon itself. These theories remind us that reality is far stranger and more wondrous than our everyday intuition allows, and that the possibilities for time travel, though filled with challenges, originate in the universe's most fundamental laws. With these foundations, we can now, once again, speculate on how space-time might be manipulated on a large scale to achieve the boldest dreams of chrononavigation. Friends, architects of the future, dreamers of distant horizons. If Einstein's relativity shows us that space-time is an elastic fabric that curves under mass and energy, the human mind, always pushing the limits of possibility, cannot help but ask, could we one day not just rely on natural gravity to curve time, but actively manipulate that fabric on a colossal scale to achieve feats of travel and chrononavigation that today seem like pure magic? Here we enter the fascinating and often speculative realm of space-time manipulation. The central idea is to go beyond simple curvature. Think of space-time not just as a sheet where massive objects sit, but as a malleable material that can be stretched, compressed, folded, and perhaps even surfaced. This concept underlies ideas born from both theoretical physics and science fiction, rooted in Einstein's mathematics. One of the most famous concepts in this area is the Alcubierre warp drive, proposed by Mexican physicist Miguel Alcubierre in 1994. This concept arises directly from general relativity. The idea is not to move a spaceship through space-time faster than light, which is forbidden, but to move space-time itself around the ship. Imagine the ship inside a bubble of space-time. In front of the bubble, space-time compresses. Behind it, space-time expands. The ship inside remains stationary relative to its bubble, but the bubble slides through the universe at an effective speed faster than light, without the ship itself violating local speed limits. For this to work, an immense amount of exotic matter with negative energy density would be required. This hypothetical matter, with anti-gravitational properties, would be crucial to create the front compression and rear expansion of the warp bubble. The energy required is so vast, perhaps the mass of Jupiter or more converted into negative energy, that building an Alcubierre drive is millennia away, if possible at all. However, the fact that it is a mathematically valid solution within general relativity makes it endlessly fascinating. And as we've seen, a warp drive's ability to alter space-time in this way could inadvertently create closed time-like curves, bringing us back to the possibility of traveling to the past. Beyond warp drives, large-scale manipulation of space-time could involve hypothetical cosmic structures, Dyson spheres, and other megastructures. While not time machines per se, these hypothetical megastructures, which surround stars to capture their energy, show the scale of engineering an advanced civilization might achieve. If such a civilization could manipulate a massive object like a star to alter its gravitational field in a specific way, the implications for time dilation would be enormous. Manipulating black holes. If it were possible to control and stabilize black holes, perhaps as wormhole endpoints or gravitational engines, an advanced civilization could theoretically generate the space-time distortions necessary for travel. Rotating black holes, Kerr black holes, already contain CTCs in their mathematical models, making them a theoretical laboratory for studying time travel. Time machines based on extreme rotation, as well as the Tipler cylinder, involve rotating incredibly dense masses fast enough to drag space-time along, curving object trajectories back upon themselves in time. Engineering a mass dense enough to rotate at such speeds is, of course, far beyond current science. The key to all these ideas lies in general relativity's ability to describe how matter and energy dictate the geometry of space-time. If we could control matter and energy on an unprecedented scale, we could, in principle, control space-time geometry, and if we control geometry, we can control time. However, the barriers are, to say the least, colossal. Enormous energy requirements. All these ideas require energy far beyond anything humanity has produced or could produce, on the scale of stars or galaxies. Exotic matter. The need for negative energy is a fundamental obstacle. If exotic matter does not exist in usable quantities or is inherently unstable, these ideas remain theoretical. Stability and paradoxes. Even if such configurations could be created, their stability is an issue, not to mention the inevitable logical paradoxes of traveling to the past. Despite these overwhelming challenges, the study of space-time manipulation is vital in theoretical physics. It stretches the limits of our understanding and asks what is truly possible within the universe's laws. It shows that space-time is not passive but a dynamic field that can be actively shaped. It reminds us that imagination, anchored in the laws of physics, can reveal technological futures that seem impossible today. And in that pursuit, we may not find a ship to take us to the past, but we may discover new forms of energy, new physical principles, or a deeper understanding of reality itself. Because, in the end, space-time manipulation is not just a dream of travel. It is an invitation to redefine our relationship with the universe itself. Friends of the unobservable, navigators of the microcosm. If Einstein's relativity dominates the vast realm of the very large, stars, galaxies, the universe itself, there is another domain of reality that operates under completely different rules. The quantum universe, where subatomic particles defy all intuitive logic. Here, matter and energy exist in a state of possibilities, and time itself seems to behave in even more enigmatic ways, perhaps opening unexpected avenues for understanding or even manipulating chronology. Think about it. In our macroscopic world, an object exists in a defined place at a defined moment. But in the quantum realm, a particle can be in multiple places or states simultaneously until observed. This is called superposition. Imagine an electron that is not here or there, but a probability wave spread across space. Only when measured does the wave collapse, and the electron appears at a specific point. This is the essence of the famous double-slit experiment, where a particle behaves as a wave when unobserved and as a particle when observed, as if reality itself depends on our interaction. But what does this have to do with time? Quantum mechanics introduces a fundamental layer of uncertainty that also affects our understanding of time. At this level, time is not a smooth, continuous flow like in relativity. In some interpretations of quantum gravity, time could even be an emergent property of the universe, not a fundamental dimension, or it could manifest in discrete, indivisible units. Consider quantum entanglement. Two particles can become entangled so that their fates are intrinsically connected, no matter how far apart they are. Measuring one particle's state instantly determines the state of the other, regardless of distance. This connection appears to occur faster than light, which Einstein called spooky action at a distance. If information could be transmitted instantaneously in this way, it could imply some form of influence challenging temporal linearity. Although physicists emphasize that entanglement cannot transmit meaningful information faster than light, and thus not enable instant communication or direct time travel, its non-local, causal nature remains a profound puzzle for our temporal intuition. The true connection between the quantum universe and time becomes even more speculative when we discuss retrocausality. This bold and deeply controversial idea suggests that in the quantum realm, the future could influence the past, or that a measurement in the present could affect the state of a particle in the past. One example is the quantum delayed choice experiment, in which the choice of how to measure a particle after it has already passed through a slit seems to retroactively affect its past behavior. This does not mean we can send messages to the past, but it does imply that quantum reality may be far more temporally interconnected than we assume. If a future event can influence a past event at the quantum level, what does that mean for the general flow of time? Moreover, some theories of quantum gravity, which aim to unify relativity with quantum mechanics, suggest that time may not exist at the most fundamental level of the universe. Rather than being a dimension, time could be an illusion or an emergent property arising from the interaction of other quantum fields or properties. If time is not fundamental, then our perception of its flow could be a manifestation of an underlying reality operating without an inherent temporal error. This resonates with the idea of the block universe, where all moments already exist. Time paradoxes, like the grandfather paradox, are difficult to apply directly to the quantum realm because at this level, reality itself is probabilistic and non-linear. In a many-worlds universe, where every decision branches into a new reality, contradictions are resolved because every possible past and future exists in its own branch. The traveler does not alter the past. They merely jump to a branch where that action has already occurred or create a new branch. Exploring the quantum universe forces us to question the rigidity of our conception of time. If particles can exist in multiple states simultaneously, and if entangled connections defy the speed of light, could time itself be inherently more blurred or intertwined than we imagine? And if this blurriness is the key to understanding phenomena we currently consider impossible, like travel beyond the limits of traditional causality, then as physicists search for a unified theory of quantum gravity, the role of time in this new physics becomes central. Is it a dimension that can be quantized like energy or matter? Or is it a property emerging from the interaction of other fundamental elements? The answers to these questions could completely redefine our understanding of chrononavigation. If time itself is an emergent quantum effect, its manipulation might require understanding and control of the universe at scales so fundamental that large-scale manipulation of space-time would seem trivial by comparison. Ultimately, the quantum universe teaches us humility. It shows us that reality at its most basic levels is far stranger, more fluid, and less predictable than our macroscopic intuition can comprehend. And in that strangeness, in that dance of possibilities and probabilities, lies the seed of new revelations about time. Perhaps time travel, if it is ever possible, will not be achieved through colossal machines, but by understanding and manipulating the secrets of the universe at its most intimate scales, where time is not a straight line, but a sea of intertwined possibilities waiting to be unveiled. Friends of cosmic mystery, stargazers, if throughout our journey we have revealed that time travel, though riddled with paradoxes and challenges, is not entirely a theoretical impossibility according to Einstein's laws and quantum intricacies, then a question arises that echoes like a sound in the void. If time travel is truly possible, why are we not flooded with tourists from the future? Why don't we see time machines landing in Madrid's Plaza Mayor or among the ruins of the Colosseum? For many, this absence is the most compelling proof that something fundamental prevents time travel, or at least its widespread use. Here, the possibility of chrononavigation intertwines with one of the greatest questions in astrobiology, the Fermi paradox and the concept of the great filter. The Fermi paradox, proposed by physicist Enrico Fermi in 1950, asks, if the universe is so vast and old, with billions of galaxies, each containing billions of stars, many with habitable planets, then intelligent life should be common. If even a small fraction of these civilizations developed advanced technology and the ability to travel the stars, the universe should be teeming with their signals, or even their presence. Yet, as Fermi asked, where is everyone? The cosmic silence is deafening. This paradox naturally extends to time travel. If an intelligent civilization can master interstellar travel, it is reasonable to assume they could eventually master temporal travel as well. Humanity, in just a few centuries of modern science, already conceives theoretically of wormholes and time dilation. What might civilizations with millions of years of technological advantage achieve? If travel to the past were possible, Earth and every era of its history should be a theme park for future chrononauts. But it is not. For many scientists, this absence of temporal travelers is one of the most unsettling solutions to the Fermi paradox. It suggests the existence of a great filter, a barrier or series of barriers, extraordinarily difficult to overcome in the evolution of life, from its origins to an interstellar and perhaps intertemporal civilization. The great filter might lie in our past, meaning we are extremely lucky to have passed it, and few other civilizations do. Or, more terrifyingly, it might lie in our future. If the great filter is ahead of us, it could explain why we see no time travelers. What could that filter be regarding time travel? Fundamental physical impossibility? The simplest reason is that traveling to the past is fundamentally impossible due to physical laws we do not yet fully understand. Stephen Hawking's chronology. Protection conjecture could be one such law. Although relativity allows solutions like closed time-like curves, CTCs, some yet unknown barrier, perhaps related to energy requirements or the nature of quantum gravity, prevents these solutions from manifesting in reality. The absence of time travelers would be empirical proof of this impossibility. Even if time travel is theoretically possible, the energy or exotic matter needed to build a functional time machine may be so far beyond any technological capability, even for the most advanced civilizations, that it simply cannot be achieved. It is as if the universe placed the time travel button at an energy level no civilization can reach before extinction, prohibition, or self-restraint. Perhaps advanced civilizations that achieve time travel recognize its inherent dangers, the butterfly effect, logical paradoxes, and collectively decide not to use it, preserving historical coherence and avoiding cosmic catastrophes. A kind of temporal directive, a non-interference code to protect universal causality. The risks are too great. The future is not what you expect. Another possibility is that travel to the past is not the type of travel we imagine. Perhaps Novikov's self-consistency principle is the rule, and any attempt to travel back becomes part of history itself, without significantly altering it. Time travelers may visit us, but their presence would be so inherently part of history that we would never recognize them as such, or their actions would already be woven into what we consider the past. Multiverse and branching. If the many worlds interpretation is correct, then traveling to the past of an advanced civilization would not bring them into our timeline, but create a new branch of the universe. We would never see them in our branch because they are not altering our past. Each journey creates its own parallel universe, leaving ours untouched and visitor-free. It could also be that time travelers do visit us, but choose to remain completely undetectable, not interfering with historical development. This would require camouflage and observation technologies far beyond our current understanding, as well as an absolute ethic of non-interference. The absence of temporal tourists is an enigma, forcing us to confront the limits of science and the implications of our boldest theories. It suggests that the path to chrononavigation is either fundamentally impassable or guarded by barriers imposed by reality itself. This question about time travelers becomes a mirror of the Fermi paradox. If there is no visible advanced extraterrestrial life and no time travelers, it is because the path to advanced intelligence is extremely rare, or because an imminent catastrophe awaits us and any other civilization reaching a certain technological level. It is a reflection that invites humility and caution. If time travel is the key to our future, it could also be the key to our survival if we understand and respect the delicate fabric of space-time. The great question is not just whether we can travel in time, but whether as a species we are prepared for the cosmic implications of such power. This question, looming like both shadow and promise, leads us to a final reflection on our place in the universe and the true meaning of our existence within the flow or block of time. Friends of discovery, architects of your own reality, throughout this astonishing journey we have dismantled the common perception of time. It is no longer the monotonous tick-tock of a universal clock, but an elastic fabric, a malleable dimension that bends with gravity and velocity, branches into infinite parallel universes, and perhaps blurs in the quantum depths. We have contemplated wormholes as possible shortcuts. We have navigated the turbulent waters of paradoxes, and we have asked why the universe seems to protect its past with unyielding logic. The great question now looming over us like a nebula of possibilities in the vast expanse is this. In a universe where time is so elastic, so mysterious, what role does our own will play? Are we slaves to fate, or conscious or unconscious, masters of our own timing? Since ancient times, humanity has debated the eternal dance between destiny and free will. Are all events already pre-written, or do we have the ability to forge our own path, to make choices that alter the future? Theories of time travel amplify this dilemma on a cosmic scale. If the universe is a block of space-time where every instant, past, present, and future, already exists, then our sense of flowing hours and our ability to choose may be mere illusions of consciousness. We are like characters in a film, living frame by frame, unable to alter the real already shot. Novikov's self-consistency principle posits that any time travel or attempt to alter the past is doomed to be consistent with original history, reinforcing a deterministic view. If future chrononauts do not alter the past because their actions are already written in it, then individual agency seems limited by the very structure of time. Your journey does not change destiny. It is destiny. It is a vision that may feel bleak to those longing for total freedom, but it also offers a profound sense of cosmic order and coherence. Yet the many worlds interpretation provides a way out. If every quantum decision, every fluctuation, every choice we make branches the universe into multiple realities, free will is not denied. It simply expands to infinite scale. Every choice you could have made, you did make in some parallel universe. In this view, we are not slaves of fate, but constant creators of many destinies. Your will is not that of a sculptor carving a single path, but of a gardener planting seeds of infinite paths, each flourishing in its own reality. The paradox dissolves into a lush abundance of existence, and this is where our consciousness, this vast and incomprehensible inner universe, plays a crucial role. As we have explored, consciousness can distort our subjective perception of time, speeding it up, slowing it down, or even transcending it in dreams and altered states. Could our mind be the key to interacting with these multiple realities or perceiving the block in a way that transcends linear experience? Consciousness could be the projector illuminating the frame sequence, or the navigator selecting the specific multiverse branch we experience as our reality. In this sense, we do not control physical time as we move an object, but we control how we experience it and perhaps which branch of reality manifests before us. Time, ultimately, is not merely a physical coordinate. It is the canvas on which we paint our existence, the rhythm of our experience, the very essence of what it means to live, love, learn, and grow. Whether our destiny is pre-written in a cosmic block, or we are constantly branching the universe with our choices, we are immersed in its flow. Our ability to comprehend it, to unravel its deepest mysteries, is a testament to the incredible power of the human mind. Perhaps we will never build a machine to physically take us to ancient Alexandria or witness the birth of a distant star. Perhaps the great filter, the enigmatic cosmic barrier, prevents us from mastering large-scale temporal travel. Yet the true wonder lies not only in technical possibility, but in our consciousness' ability to transcend apparent limitations, to conceive these ideas, to feel the elasticity of time in moments of ecstasy or despair. Every time you reflect, gaze at the stars, feel the weight of a memory, or glimpse the promise of a future, you are dancing with time in its deepest forms. You are exercising your will within a temporal framework far vaster and more enigmatic than you ever imagined. We are not merely products of time. We are, in a profound sense, its experimenters, its dreamers, its observers. Time travel, in its deepest essence, is not science fiction, but an invitation to redefine our relationship with reality. It is an opportunity to awaken to the astonishing truth that the universe, with all its mysteries, is far vaster and our existence far more interconnected than our linear perception allows. And in that understanding, in that expansion of consciousness, lies true freedom. So, observers of reality, if this journey through the invisible threads of time has resonated with your spirit, if it has sparked awe and an insatiable thirst for knowledge, I invite you to continue this exploration. Join our community at the Quantum Observer. Your subscription is not merely support, it is a statement that you are ready to challenge the limits of the known, to contemplate the unobservable, and to unravel the universe's most fundamental secrets alongside us. Because in the end, time is the greatest mystery, and by exploring it, we discover not only the cosmos, but ourselves within infinity. The tick-tock continues, and with it, our unceasing quest for truth.